So let me get started. First thing I want to mention is that I saw a question on there about that really applied one of the projects that, and specifically to classwork, and that was about how to display information graphically. And problem with displaying information graphically is that just like everything else we do in statistics, it depends on what the variables are, what kind of variables that you're working with. Okay, so I know somebody was trying to plot, produce a scatter plot, but they were using nominal data. In fact, I think binomial data, but right. So that's not going to work very well. So let's take a look at why. Let me open up a familiar database, so I don't have to go looking around too much. I have a couple of others here that we can work with as well. Okay, so it doesn't seem to have opened, eh? Okay, try this again. Oh, no, that's not. Let's not close it. Let's try reopening it. Here we go. Okay. That looks like I opened it twice, but that's okay. All right, so let's start with, for instance, if we have two categorical variables. Let's start with gender and marital status. I think marital status is only two values. Let me just check it in here. Marital status is indeed only two. Both of these are two values. That they're so basically they're binomial variables. If I try and graph these using scatter dot graphs or scatter plots, I'm going to move in the gender of the child, and I'm going to move in the let's see, marital status of the mother, and we're going to wind up with something that really doesn't give us too much information. In fact, oh boy, it should run it for us. There you go. You wind up with four dots, right? These are represents people that are, I guess, that it was a female baby and married mother or something like that. It doesn't give us any kind of information, right? So when we want to look at categorical variables, that whether they're binomial or not, chances are what we really want is we want to produce probably like a bar chart or a pie chart. Pie charts aren't particularly favored very much in uh, 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 in statistics. So probably you want to produce a bar chart. So basically, if we're interested in measuring the gender of the how many women, how many married women had male children versus female children. Let's give this a try. Let's see, gender. Where is it? Marital status of mother. I'm going to put that into the category axis, the x-axis. I'm going to put the gender of the child into the. Actually, you could even use numerical variables here. Actually, so well, let's see what happens if I try and move that. No, well, let me move that in. Okay. Mother. Come on, let me move it in. Oh, I'm sorry. I moved this into the wrong section. The marital status into the rows, and I never really produced. I'm using the legacy dialog for this particular type of graph. Marital status rows, and in columns, let's put the sex of the child. That's the kind of graph we wind up with. Number of cases. Uh, let's see. I am not getting male children versus female children. Variables. Let's see. Oh, panel by rows. Move this into here. Okay, there we go. Okay. So among married women, so we got two nice bar charts here produced. Among married women, we can see relatively what the relative number of uh, uh, male children is relative to female children, and for unmarried women, we can see the relative number of male children to female. So it looks in both cases that there are a higher percentage of males that are born than female children, right? I think that's pretty much the case, nationally or in terms of the world, unless there's some kind of intervention to affect that, right? So when we're dealing with categorical variables, chances are you want to look for bar charts or a similar way to display it. When we're dealing with two numerical variables, that's when we get into scatter dots. And the reason for that is that each value, each subject is going to be displayed as an XY coordinate. So for instance, if we want to plot, let's pick a numerical variable here. If we wanted to plot the mother's age against the amount of weight gained during pregnancy, we would use a scatter dot, right? Because each one of these mothers would then have a single value. For the data view, each one of the mothers would have a single value for those two numerical values. For instance, this mother is, let's see, her age is 25, and the weight gained, that's unusual, 75 pounds. This mother gained 25 pounds, and she was 15 years old. I'm really picking out some of the more extreme values here, 21 and 28 pounds. But in each case, one of these could be defined as an X value, value, and a Y value for each individual point on a graph. So let's do that. Graph, legacy dialogues, scatter dot, and I'm going to choose scatter dot, and I'm going to move those two variables in here. I'm going to put the age of the mother in rows. And I'm going to put, oh, I already have it. I already have it up here. X and Y axis is already defined. I'm going to get them out. Okay, it must be a carryover from the previous analysis. Okay, I'm going to put the mother and the X values. I'm going to put the, let's see, the weight gain during pregnancy, see if there's a correlation between these two. We're going to talk about that momentarily. Okay, so we produce a scatter dot, and each one of the dots here represents an individual mother, right? And plots their age against the amount of weight gained during pregnancy. And it doesn't look too promising in terms of correlation. Let me just take a quick look at it while we're here, so I don't waste time trying to see if there's, yeah, the R squared, R or R squared are both very, very small numbers. Notice how this is basically a horizontal line. So it looks like the age of the mother has almost no influence on the amount of weight gained during pregnancy. Right? Pretty interesting. This is live data. It's a small subset of all of the births in North Carolina during that particular year. Excuse me, during that particular year, but it's still, still actual real data. So occasionally we're gonna wind up with stuff that makes some sense. Okay. Now another important plot that displays a lot of information for us is going to be when we want to look at numerical data that's compared by category. For instance, in the case of this data set, if we wanted to know whether there was a difference in the let's get a big number here. Wanted to know if there was a difference in the weight gain during pregnancy versus marital status. Okay, so let's take a look at what we might do there. Well, the marital status is a nominal variable. It's a one. I think it's a 1 or a 2. Let me turn the values off and on. Oops. Marital status is a 1 and a 2, and of course, the weight gain during pregnancy is a numerical variable. Okay, so we want to see if there's an association there. We want to demonstrate that graphically. So let's go to analyze. Oops, actually, let's stick with our graphs. Again, I'm not used to going to legacy dialogues and doing this, but let's take a look at what we might have here. How about a box plot? Right, box plot seems very familiar with this kind of analysis, doesn't it? Because we're looking at two different groups, married women versus unmarried women, and we want to see the comparative distribution of the values for weight gain. For instance, the median weight gain for these two groups to see if there's a difference. As it happens, Boxplot uses median rather than mean. Okay, so let's see. In the variable that we're looking at is the numerical variable, the amount of weight gain during pregnancy, and the nominal variable is going to be the weight. The marital status of the mother. Okay, let's take a look at what that graph looks like. Okay, and here we go. Well, in fact, it gave us some results here, didn't it? Okay, we can see comparatively where the mean is, what the 50th, the interquartile range is, what the overall range is. If we have outliers here, one of those was actually that's got to be wrong, right? Excuse me. That was each one of these numbers, the way it's currently, you can change this. In fact, and actually show the real values if you want to. But the way it's displayed right now, that's the subject number. That's, in other words, when we went back there, we find that potential outlier is the 750th subject in this list of 500, in this sample of 800 subjects. Okay, so if we look at this, we can see there's a bit more variability among the women who are not married. I'm not so sure about, like 0 doesn't make much sense here. That's probably a missing value rather than really, one of these recorded as 0. It's probably not really the true minimum value. This is the maximum value with outliers identified and so on and so forth. And the median is the middle bar here, 25th percentile, 75th percentile. So when they're side by side like this, it allows us to examine the variability. It allows us to examine where the middles are, where the means or the medians are, and even whether they're skewed or not. So for instance, in both of these, the median appears to be right in the middle of the interquartile range. So it doesn't appear that these are very skewed. Okay, so let me see if I can't find one that's a little bit more interesting. Let's see. Let's see, marital status. How about smoking? Oops. Let me smoke during pregnancy versus weight of child in ounces. Let's get a look at what that looks like. See if that's a little bit more interesting. Well, actually, it's a little bit more interesting. See, we can see that that's pretty interesting, right? Now, you can see that there's a lot more outliers here for women who smoked who did not smoke during pregnancy, but the median value. This could just be because there's just simply many more women. I'm thinking maybe the reason for all these outliers is that there's so many more women in the group that smoke during pregnancy. But let's take a look at the median. The median weight is for of child born to mothers who didn't smoke is a bit higher. It looks like it's significantly higher than for mothers who didn't smoke during pregnancy. So we have a little bit of an idea of what this looks like. In both cases, again, except for these outliers here, they look fairly normally distributed. And this probably represents premature births, I would think. So, okay, so there's the short story here is that when you want to display data and communicate, displaying data graphically is a great way to communicate information. When you want to display it, you got to make sure that you use the right type of graphics for the variables. Determine whether they're categorical, nominal, a combination of categorical and nominal, and so on and so forth, and decide which one you're going to use. Okay, but in general, scatter dots usually display. You're almost always displaying numerical and numerical variables. Okay, let's get to some analysis. Oh, one other thing. As you're doing your reports and your projects, you may also want to consider that with the database that you're working with, you may want to go and use graphics to describe the population or the sample that your population, that you're drawing from your population, okay, as a way of kind of like, describing the overall population. So for instance, you may be interested, if it's a numerical variable, you may be interested in making sure that you are able to, let's see, that you are, let me go into Explore because it'll allow me to do some graphics as well. Description statistics Explore. So for instance, we were just talking about the weight of infants at birth. So let's see, weight of child at birth. I put that into our dependence list. I can go ahead and I can ask SPSS to produce some plots for me, including a histogram, and it's going to automatically produce that box plot for me as well. So I'm going to go ahead and say OK. So this will give us an idea of, there's a box plot for all of the, notice I didn't break this up into groups, I didn't factor this, but it gives me an idea of what how the data looks for all of the infants, the mean value and the distribution, the outliers, and so on and so forth. Did I check? I thought I checked off histogram there. Statistics, Explore. Let me go back and take a look. Plots. I did check off histogram. It didn't do it. Maybe because Explore wants me to put in another value so I can break it up into groups. So if I want to separate this and produce graphics for the weight of the child based on marital status, it'll break it up into different groups for me. Histograms chosen, and I got both chosen. Let's give this a try here. Okay, there you go. Now we have histograms for the weight of the child, and notice that it's skewed because of premature births. Okay, and this is for the weight of the child in ounces for women who are not married. Again, skewed to the left. We saw those outliers there. You have to decide whether or not you want to include those very low birth rate babies, premature babies, depending on what kind of analysis that you do. And you could do this as well graphically using Chart Builder, so on and so forth, or just going down here and asking it to produce a histogram for you. Okay, and let's see, variable, let's see, just do the age of the mother. Let's see if it'll produce just for all of the variables hit. That's for the entire population, where my previous analysis going to analyze it would not give it to me unless I put in a factor value. With that, at least it'll do all of the women in this population. Youngest was 15 and the oldest was apparently 42 in this sample. So descriptive statistics will help you in describing the distribution of information in your data set. So that might be part of one of the things that you are considering doing in your analysis. Okay, so let's talk about let's work our way backwards through the statistical analyses that we were learning. Okay, and let's start with correlation or regression. I'm going to close this. Okay, good. These are some of these data sets are actually installed on your computers. Let me see. It's a question there. Is the project posted yet? Jolanda's I think she's in the online course. There is some information on that posted. Your project is a lot more modest than the guys that are in the brick and mortar course. That one's been like a semester long mission. Actually, now that you mentioned it, I'll post a bunch of information about it because in the online course, you're going to have an option of doing a very brief project or doing a third exam in the online course. So the other guys here, I think, are mostly from the brick and mortar course, if I'm not wrong. Okay, but I'll post something today about that. Okay, so that you guys are updated. But there is some material on Blackboard now, but I won't worry about it too much. Yours is a lot more modest than theirs is. So okay, so I wanted to mention that there's a number of these data sets that I have in front of me right now are actually data sets that came with your version of SPSS. There's a folder in your installation, in your program folder that includes a whole series of data sets. I'm going to use one of them right now. It's called ozone. I use it mostly because it has several numerical variables. And since we're talking about a correlation regression, we know that that's kind of a statistic that we apply to numerical variables. Okay, so I need a few of them to work with. Okay, so here we go. Let's see what we have here. Okay, so this looks like, I'm not sure what VH is. Let's see if we can get to the variable view. Not sure what VH is. They don't define it here in the label, so I'm going to ignore it for our purposes. But ozone is the daily ozone level. Inversion base height is a weather measurement. Pressure gradient is the amount of pressure, the atmospheric pressure. VIZ is visibility. We have the temperature, and we have the day of the year. Okay, so I'm not sure day of the year is probably going to be relevant to us so much, but let's see what we have it here. Here's the day of the year. These are days that they took these various readings. So I want to see if there's a way for me to use these atmospheric measurements that probably the weatherman you can get from the weather every morning if you really looked hard enough or online. If I can use them to predict the ozone level. Now, ozone, you would need a tool to measure that. You would need some mechanism for actually measuring the ozone levels outdoors, where this information may be part of ordinary weather collection. Right? So I'm going to say to myself, gee, it would really be useful for me if I could see if there's an association between these various different variables. The inversion, in other words, what the cloud layer is, what the inversion base layer is, what if there is how high a temperature gradient goes, the pressure gradient, in other words, the barometric pressure, the visibility, the temperature, things I might be able to find pretty easily online or measure pretty easily from the ground, if that has some influence on the daily ozone layer. Okay, so let's see if we can't use these values to predict the ozone layer. So the first thing I want to do is I want to see if there's some way for me to see if there's an association between these. So since we're dealing with numerical variables, numerical versus numerical, numerical versus numerical, well, one of the ways I might examine that graphically, of course, is what we just talked about, is going to be our histogram. Okay, so I'm going to click. I'm going to click on I'm going to click on simple scatter plot first, and I'm going to take one of these at a time. I'm going to take daily ozone layer, and I'm going to put that into the y-axis. Right, that's what we're interested in, and I'm going to put the inversion base level into the. Actually, let me take the temperature and put that into the x-axis. Let's see if there's an association between the temperature and the ozone level. Okay, let's plot this and see how it looks. Wow, that seems like a pretty significant association, doesn't it? Okay, and I'm going to just apply a best fit line to it. Okay, by the way, what I did there was, let me go back and show you what I did there. What I did there, that line wasn't there when I started. What I did there was I double-clicked on the chart. It opened up an editing window. In this editing window, I can go in here and edit the fonts. I can edit the text that's in here. I can change colors and so on and so forth. But I can also choose to do some quick graphical analytical tools. Like this one applies a best fit line. It's a little weird, the nomenclature they use. Right, it applies a best fit line. I just think I just did the wrong one there. Okay, I already did it before, so let's see. Fit line the total. Yeah, that's the one I want. So the second time I do it, it's giving me a different interpretation than linear. The first time you do it, it'll give you linear. And if I can't undo it. Okay, so assuming this relationship is linear between me and you, that's a little bit of a stretch here, as we can say, right? See, and in fact, when we tried to redo that, we do that from scratch, so you can see it really gave me that line to start off with. Okay. Again, I'm going to double click into this. I'm going to ask it to produce a best fit line, a linear best fit line. And indeed it does. Okay, I think if I click it again, it's going, oops. No, let me do it now. Okay, let's see. If I go in here, oh, it just creates, it makes a different selection on the, on that chart, on that box that opened up. But to actually try and fit it better with something that's other linear. But since we're only working with linear regression right now, I'm going to stick with what I have here. Now R squared is points, we can see just visually that this looks like a very good association or a very good correlation. R squared, we're going to be discussing in a second, is 0.6. That's actually a pretty high number, right? So this is a very satisfying result. Well, now I can do this and I can repeat this again for graphics, legacy dialogues. I'm going down scatter plot. I can repeat this again, and instead of looking for an association with temperature, I can see, is there an association with the visibility? Yeah, there's some measure that they use, some numerical measure that they're using for visibility, might be miles or something like that. Well, this one's a little bit more tenuous, right? Because first of all, it's group data, right? So let's see if we get a fit line here. Okay, and it looks like as visibility goes down, as visibility goes up rather, the ozone concentration goes up. Does that make any sense? That as the visibility goes down, the ozone layer, as visibility goes up, as visibility in miles goes up, the ozone uh, uh, content in the air goes down. That's kind of counterintuitive to me. You know, I would have thought, there's good cloud cover, that maybe ozone layer would be lower. Maybe this isn't measuring cloud cover. Maybe it's measuring horizontally through the air. So when there's a lot of smog or haze, like you might get in California frequently, or in big cities in California, and say all of California, that maybe as that haze gets greater, not cloud cover, but haze gets greater, that in fact the ozone layer, the ozone levels go up, and the portion here where the haze is greatest is where the visibility is lowest. Again, looking forward, not looking up at the clouds. Okay, so there's several factors here look like that, and this also seems to have some association, some graphically visible association. So let's take a look at this in terms of whether or not we can see if these associations are significant. Let me try one more thing here. Let's go into matrix. Okay, and this time I'm going to let's see. I'm going to move my all of my variables in here to see a number of different associations. And it's going to produce a haze of information here. So this actually is allowing us to look at the daily ozone layer in relation to the distribution of the data for the inversion base height, the the barometric pressure, the visibility, right? We can see visibility is going down, and we can see a nice correlation here with temperature, not so much with the pressure, barometric pressure, and it does look like there's an association here with the inversion base height. In other words, if there's a thermal inversion, like how high it is. Okay, so I got at least 3 of these seem to have some good, strong association with the daily ozone level. This is just a way for me to get a quick look at comparing many of these different variables to each other, so I can look for interesting associations. Again, sometimes, just like a lot of things in SPSS, when we see the outputs, we can actually see that it's trying every permutation. So we see the ozone level versus temperature here, but we also see it down here as well. See the mirror image, right? And that's why That's why these boxes in the middle are empty, is because in those boxes you're comparing something to itself. Ozone layer to ozone layer, ozone level to ozone level, uh, uh, pressure to pressure, and so on and so forth. Okay, so that's a quick way of taking a quick look at these things. All right, so let's actually take a look at the numbers here. The first thing I want to look at is whether or not there is a significant association between these variables. So I'm going to say analyze. I'm interested in whether there's a correlation, a numerical correlation between the numbers for these. So I'm going to go to correlate. I'm going to go over to bivariate, okay, two variables. And I'm going to say, I want to take a look if there's an association between the ozone level and the temperature. Okay, it's one of the first ones we looked at. I'm going to click OK. And this will calculate for us a Pearson's R, or Pearson's rho. Okay, and that'll give us a number between -1 and +1 for the correlation between the two variables. Right? So what do we wind up with? Pearson's correlation, or R, turns out to be 0.781. If when we have 0, we have basically what we would call no correlation, or zero correlation. There's no association between the two of them. When we have a number other than 0, it suggests that there's some association. Of course, because this is a sample, like everything else we do in statistics usually, since it's a sample, well, we're not always going to get exactly 0 if there's no correlation. Chance may give us something that looks like a minor association, right? So what we need to do is we need to look at this number here and interpret it in terms of that range, 1 to -1 to 1, passing through 0. So it doesn't look like it's 0. It looks like it's quite a bit different than 0. The other thing is it's a positive number rather than a negative number. That indicates to us as one variable goes up, the other variable goes up too. In other words, the level of ozone, as the temperature goes up, the level of ozone in the air goes up as well. Seems reasonable, right? In summertime, we have more issues with the ozone level than we do in the wintertime. So that's an interesting association, right? And it looks like a very strong association, right? That's a number that's pretty close to 1, right? So it's a strong positive association. Now, is it statistically significant? Well, yeah, let's take a look at it. Now, that the probability of this happening by chance is 0.000, less than, which is not really 0, it's less than 0.001. Right, so that's how SPSS is going to describe it. So what does that mean, that statistical significance? Well, remember, just like everything else, we have a null and an alternative hypothesis. In words, our null hypothesis is that there's no association between the ozone level and the temperature. Our alternative hypothesis would be is that there is an association between the two of them. Well, how would we write that symbolically? Symbolically, we would say R, the R value, Pearson's R value, is equal to 0 as our null hypothesis. We're assuming that there's no correlation, or it's 0. And our alternative hypothesis is that it's not equal to 0. R is not equal to 0. Okay, notice that's two-sided. In other words, we don't predict whether it's a positive correlation, both go up, both go up, or a negative association, as one goes up, the other goes down. Right? We don't really care about that at this stage. We're just testing for the association. So this is a particularly strong one, and it looks statistically significant. Now I could go through all of the rest of them as well. Actually, let me see if I can't. Bivariate. Let me add a couple of these others in here and see what I wind up with. Okay. Okay, daily ozone level versus daily ozone level. That's a Pearson's correlation of 1. Well, we're comparing it to itself, aren't we? Right? So I just loaded all of them in there at once so I could test the correlation values for all of these variables against each other. So daily ozone level, the correlation is 1. Since I'm comparing it to itself, you would expect it to be 1, right? Whatever, it's the same number, right? In terms of comparing it to temperature, well, look, there's a strong positive correlation. Well, inversion base height, there's a strong negative correlation. In other words, the higher it is, the lower the ozone level is. The lower the inversion is, the lower that that level of air that's trapping nasty gases close to the ground, the lower it is, the higher the ozone level is. So that's a negative association. Pressure gradient. The higher the barometric pressure is, the higher the ozone level is. Right? Higher barometric pressures are probably associated with certain kinds of fronts. So maybe they're more likely to be a thermal. I'm going to get to this in a second. I'm going to come back to that, but there's reasons why this might be true. But the pressure gradient, the pressure is higher, barometric pressure is higher, more like the higher the ozone level is likely to be. And visibility, again, this is looking horizontally, not up to, it's not cloud cover, right? So the higher the visibility, the less smog there is, the less material there is in the air, less photochemicals there are in the air, and that would suggest that the ozone number is lower on those days, right? Now, which of these are statistically significant? Well, look, 0.000, 0.000. They're all statistically significant. They're all less than a p of 0.05. Remember, our standard for rejecting the null hypothesis is that the p-value, the significance, has to be less than 0.05. In other words, in each of these cases, there's less than 5% chance of being wrong if we reject the null hypothesis. Okay, so now let's put this to work for ourselves. We have 4 nice variables that appear to predict the ozone level. I'm gonna pick the one that looks like it's the best predictor to go on and do a simple linear regression. Okay, so I'm going to say analyze. I'm going to go down to regression, and I'm going to go to linear. Okay, so let's put something in here. Let's see. The dependent variable is the one that I want to predict. So in this case, I want to predict what the ozone level is. Right? In regression, we're taking our correlation, our relationship between these two numerical values, and we're trying to turn it into a formula that we can use predictively. So we want to predict what the daily ozone level is. That's what our objective is. So I'm going to say, let's take the temperature and see if that allows us to predict effectively predict the ozone level. Okay, so I'm going to click OK. And let's take a look at what we have. So we run through a series of analyses. And the first thing it does is it repeats our correlation. Right? Our correlation is 0.781, as we saw before. And that it's, here's our R squared. It took that number and it squared it. I'm going to come back to that value. Again, that number is just derived from our R value. Just 0.781 squared is 0.609, about 61% of 0.61. Okay, our statistical analysis for this association is a p-value of 0.000. We saw that summarized in the correlation chart before, right? So we know that there's an association, right? It's a very strong one, and that's statistically significant. Now, in addition to its regression, what it does is it takes that line that we drew for this this best fit line. And the way this best fit line is generated is that each one of the differences between each value and where this line is, in other words, for a day when the temperature is 80 degrees, I'm going to take a warmer day, when temperature is 90 degrees, right? Well, this value is just that much different. This value is this much different on the y-axis. In other words, in terms of the daily ozone level in whatever that is, parts per billion, right? And we would take each one of those differences and square it. And the objective here is to draw that single line that takes the sum of all of these squared differences from what the line says to what the actual value was, and balance them. So half of them are above and half of the total is above, half of the total is below. That strategy is going to give us a single line that we can all agree on, right? And also give us a line that's going to help us predict, give us the best prediction for how this variable, the independent variable or the predictive variable, affects the dependent variable, the ozone layer. Okay, so let's go back to our analysis here. Okay, so what these coefficients give us, and it does this analysis, and it draws this line without actually showing it to us. It draws this line or calculates this line. These coefficients tell us, first of all, the significance of these, statistical significance. We know that already that they're likely to be statistically significant. Okay, give us the values that represent that line. Now, in order to represent a line, we need two pieces of information. Two simple pieces of information will tell us, will produce for us a unique line. If we know these two things, there can only be one line that actually represents that. I can't. Okay. Okay, so what are those two values? Well, when we're back in taking algebra, we used the formula y is equal to mx plus b. We knew that if we drew a line, and this was the x-axis, this is the y-axis, the place where that line crosses the y-axis is when x is equal to 0. That's called the y-intercept, place where the line crosses the y-axis, right? So if I know that the line crosses the y-axis there, right? Well, I'm going to call that my y-intercept, right? When x is equal to 0, y is equal to this value, this height, right? Y is equal to mx plus b. If x is 0, if it's 0 on the x-axis, then all we're left with is the y value. That's the y-intercept, right? So we know it goes through that point. Okay, so now if we know what the slope is, in other words, the slope represents, for a line, the slope represents the amount of change in the y-axis over the amount of change in the x-axis. Change in y, delta, change in x, it's equal to the change in y over the change in x. In other words, how big the slope is. The slope of 2 looks like that. Slope of 1 looks something like that. The slope of 0.1 looks something like that. 0.1 would be very little change in y for the big change in x. So if we know what the slope is, right, then if we know it goes through that point, then that line can only have that appearance, right? Every line that we would draw is going to have a unique y-intercept and a unique slope, right? So this formula describes all lines. Okay, so our line, if we want our lines, for instance, this line, right, which has a slope of 1, for a change of 1 in the x-axis, change of 1 in the x-axis, y is equal to mx plus b is going to be equal to, well, x is 0, so it's just going to be 1, it's going to be equal to x, right? If it goes through up here, right, it's the same slope, goes through up here at 2, it's going to be equal to y is equal to x plus 2. If a slope of 2 for every 1 we change in the y-axis, it changes 2 in the x-axis, is going to be y is equal to 2x plus 2. So we can always identify that line by that kind of formula. So let's take a look at what we have in our regression. In our regression, we found that the slope, the relationship slope between the temperature and the ozone level is 0.433. For every 1 degree of change in temperature, you have a roughly half a part per billion change in the ozone level, right? So, and that's roughly going to be true through the entire range of data that we have. Right? We only worked with the range of data that we actually have. Okay, and it's statistically significant. This other number, the constant, represents, and as you would expect, the constant represents our y-intercept. What's the value of the ozone when the temperature is 0? You know, a lot of times this y-intercept will not really exist. It'll only be a number that we need to construct our line because it won't make any sense. So, for instance, if we're looking at infant births, right, and the x-axis and the x-axis represents the weight of the child at birth, right? 0 doesn't make any sense, right? If we're looking at adult blood pressures, a blood pressure of 0 doesn't make any sense. There's not going to be an adult with a blood pressure of 0, right? So this Y, in some cases, it can be one of the values that you're working with, but in a lot of cases, maybe even in most cases, it's just a way, an anchor for our formula, right? We don't really use it to represent an actual possible value. So let's draw our graph. Okay, so what do we have here? We have X and a Y axis, and we have, let's see, on the X axis, we have our independent variable. That's our temperature. That's the one that we're using to predict the other. In the dependent variable, the Y axis, we have our level of ozone in parts per billion. Okay, so in this case, it goes through minus 14. So actually, if we ran this all the way back to temperature 0, it would look something like this, right? The slope really doesn't represent anything. So we're not really interested in any of this part. We're really only interested in this part up here. So this formula is going to be, the formula that represents this line is going to be Y is equal to the slope, 0.433 times X plus, plus, which turns out to be a minus, right? It's a minus value, minus 14.937. I'll put 14.9 for right now. Okay, so this represents the relationship between temperature and ozone layer based on the best fit line that we drew for the graphical representation. Okay, well, what is Y? Y is, I can now substitute just simply what the values are that we're working with. The temperature is equal to 0.433 times, the ozone is equal to 0.433 times the temperature minus 14.9. Okay, so now we would plug in the temperature here. Now the temperature, now you guys, I don't know, I don't know if any of you guys have taken much environmental science, but they gave us the temperature in degrees Fahrenheit, and we got a nice correlation with that. But you want to know something? Gee, maybe we should have used absolute temperature instead of like this kind of artificial, a European Fahrenheit scale, right? So I'm wondering maybe we should have converted it. But to be honest with you, we're not worried about. We're not in environmental science right now. We're in statistics. So I'm going to leave it just the way it is. But at any rate, so let's take a look at this. So we can use this formula now, right, to predict the ozone level. If the only thing we know about the weather conditions right now, temperature is so let's say it's the winter time, temperature is 32 degrees outside, right, 32 degrees Fahrenheit. Well, we plug it in here. Let's see, 0.433 times 32. Point 433 times 32 degrees Fahrenheit, okay, is equal to 13.8 minus 14.9. Okay, we're going to come up with a funky number here. It's going to suggest that there's not much ozone in the air. So you want to know something? Maybe the temperature range down here didn't go down that low. Yeah, as a matter of fact, you can see that it crosses the y-axis here. The data is almost all above 32 degrees. So this data is probably drawn from California, right? So not often, Southern California doesn't get freezing weather very often. So that's a bad example. Let's say we're looking at a temperature of 50 degrees, a cool day, a freezing weather day in Los Angeles might be 50 degrees. So let's try that now. 0.433 times 50 is equal to this, minus 14.9 is equal to 6.7. So we're predicting that based on that temperature, the outside ozone level is going to be 7 parts per billion. Well, if you're asthmatic, you have pulmonary function issues, and so on and so forth, that might help you to determine whether you're going to have a breathing issue that day or a lung irritation issue that day. Now, how about on a hot day when it's 95 degrees? On a hot day when it's 95 degrees, the same calculation, 0.433 times 95 minus 14.9 is equal to an ozone level of 26, which is really high, right? Which could be really irritating, right? So what does that tell you? That tells you if you have if respiratory problems and your lungs are irritated by high ozone levels, that if it's a hot day in Los Angeles, maybe that's a better day to stay home. And that probably is what most pulmonologists would tell you, that there are certain days when, if you have pulmonary function issues, that it's better, whether it's because of pollen or ozone or other factors, that those are days that maybe it's better to stay indoors to avoid these high levels outdoors. Okay, so we would use that formula, right? Remember, temperature in this case is uh, uh, is our independent variable or predictor variable, and ozone is our dependent or predicted variable, the one that we want to predict. Now, I want to show you something else here, and that is that, we have all of these values in our data set for, not this one. Let's get rid of this. Oh, no, I don't want to do that. What happened to my data set here? Go. Ozone, here it goes. Okay, there we go. We have all these values in here, right? For ozone level and temperature and so on and so forth. One of the things we might be interested in doing now is seeing how good it is. We actually measured on the dates for which we have data, which is what we drew on to create our formula. We actually have a measurement of the values for the ozone levels on those days. So I'm going to go in here and I'm going to say, I'm interested in seeing how good a predictor each one of these values was. So I'm going to go here to analyze, and let's see. I'm going to go down to regression. I'm going to go into linear regression, and I'm going to say to myself, I'm interested in some other information here. Like, for instance, how close does our formula that is produced by our linear regression, how closely does it predict each one of these different values here itself? If I applied the formula to the data that I already know, in other words, I already know that the ozone level was 4 there. Okay, so let's go in here to save. Okay, and in here, I can ask it to save the predicted values. In other words, to apply the formula to each one of these values and tell me whether or not, tell me what the value would be if we used our new formula to predict this. Okay, and not only that, I can also tell it to tell me what the difference, do the math for me. What's the difference between that value that was actually measured and what our formula predicts? I'm going to call that residual. That error is called the residual. Okay, and that's that difference between each one of those, that line, each one of those values, not squared, but the difference. Okay, so I'm going to ask it to give us both of those values. Calculate that for every sample that we have here. I'm going to say continue, and I'm going to say okay. It does our analysis again. This doesn't look any different than what we did before. It has some residual statistics, right? But if I go back to my data set, well, here is our predicted values, and here are our residuals. Okay, let's take a look. That means for this particular subject, let's get this guy here. Okay, that means for this particular subject, we predicted an ozone level of 8. The actual ozone level was 4, and the difference was we missed it by 4. Okay, for this person over here, well, we got very close with this person, right? We predicted, we predicted 2.36. It was actually 2. That worked out pretty well. How about this person here? Okay, the residual is only 1.47. We predicted 4.5. It was actually 6. Right, so we have an idea of how good we are predicting from the same values that we had before. One of the interesting things about this is that if we plot these residuals, we want to demonstrate that they're not skewed, that the errors are random. I'm going to go back to my chart here, my output table. on my chart. I don't see my output table anymore. Yeah, I lost my output table. There it is. Okay, I'm going to go back here. And one of the things that we're interested in here is that we want to see that these errors are the same at the top and the bottom and the middle. In other words, these errors are not predominantly on one side on the top, that they're randomly distributed across this line. Looks like a little bit of a problem here, doesn't it? Doesn't look like it's completely linear here, right? Because it looks like up at the top that the temperature is having more of an influence than it did at the bottom. So maybe it's not, maybe we're bending the rules here a little bit by saying this is that this is this is normally distributed, and that this is really linear, and then the errors are normally distributed, right? So I'm a little uncomfortable with that, but at least now we know that we might have a little bit of an issue here. The other way that you can see this is by checking to see whether your residuals are normally distributed. In other words, most you would expect most of them to be closer to zero, and fewer of them to be extremely far from an error of zero, right? Just like any normal distribution, you would expect not that big a difference. So you could plot these and see if they're normally distributed. And instead of plotting the actual values themselves, you could actually go to Analyze, Regression, Linear Regression, and you could go into the plots here. And remember, excuse me. And remember, I mean to say, remember before, one of the options that we looked at here was to plot the predicted values that we have if we apply our formula, the actual values, and give us another column that gives us the unstandardized values. Well, instead of that, you could ask it to plot the standardized values. In other words, to give you the z-scores for each one of the values that you predicted. So I did it again. So this time we have the residual, but the residual reported in a way where you took the residual values and you calculated a mean and a standard deviation for them, and you plotted the z value for each one of these things. So now you can plot these on a histogram, and you could see if it looks like they're normally distributed. Yeah, I'm not going to go into too much of that now. We're running a little later here a little longer here on linear regression. Actually, tell you the truth, I'm glad we spent so much time on regression, because my understanding is that for these brick and mortar people, that regression is going to be an important part of your project. Okay, that's going to be expected to perform at least a regression analysis. So for you guys, if you guys in the online course, you're going to be doing, you're going to have a choice of doing a brief project or taking that third exam. And the third exam is going to be principally on regression. So one other thing here that we covered in class very briefly, and that is the idea is that there's more than one, we could go back here and we can run a regression analysis again, except this time we can use one of the other independent variables that we thought were good predictors, like visibility, except it predicts it the other way. We could run that and get a new formula based on just visibility. Well, gee, wouldn't it be good to combine several different independent variables to see if they give us a better predictor of the ozone layer than just that one variable that we're working with? Let's give that a try. Let's take, what was the first one we took? We took temperature. Let's take our visibility. Let's take our barometric pressure. Let's take our inversion base layer. Let's use all of those factors together. You could just use 2, 3, 4. You could experiment with this. Let's take all of those factors together and see if it improves our predictability. I'm going to click OK. Now let's see what we wind up with here. Well, now I wind up with a formula that has several different values here, several different coefficients here. So let's take a look at this. Okay, now let's go back up here. Look at our R value. Our R value before was about 70.7 something, and our R squared was 0.60, right, about 60%. Now it's 0.67. So I think now it's a good time to mention that this value, this 0.61, that R squared predicts that 60%, 61% of the variability in the ozone number is predicted by the temperature. So 61% of the variability in what our outdoor ozone level is can be predicted by the change in temperature. Okay, well that's pretty damn good, right? That looks pretty good. Well, in fact, now that we included these other variables, right? In fact, now it looks like we've improved our model. Now it looks like we can predict 67% of the variability in the ozone level by adding these other variables. Okay, so let's take a look at this. Where did my coefficients go? Okay, here are our coefficients. Okay, so now our formula looks a bit different. Notice they're all statistically significant still. Now our formula now takes a slightly different form. Well, quite a bit of a different form, right? The form that it takes now is we have 4 values for x, 4 independent variables, predicting our ozone score, right? Our ozone number. We have a single constant, which is our y-intercept, and we have 4 values. So how would we describe those in a formula? Let's get on here. Let's get a new sheet of paper. And let's take a look at what these look like now. Okay, so now our formula, our independent variable y is equal to b, our y-intercept, plus x, the slope 1 times x1, our first variable, plus slope 2 times x2, and so on and so forth. So in this case, y is going to be equal to negative 4.98 plus 0.33 times temperature, our first x, minus 0.011. Doesn't look like it's going to have that big an influence on our. Actually, you can't really tell because it depends on what the size of the magnitude of the units that they use. So miles could be hundreds of miles. So that could turn out to be a significant factor, right? Times miles, minus this times miles, plus, and I can't display more right there in one line, plus 0.022 times, and what was that variable? That variable was pressure, right? Pressure, millimeters of mercury, probably, plus or negative minus 0.001 times, and what is that? That is the inversion base height level. Inversion base height, I'll put IBH. So this formula now is our regression analysis formula, right? So what does that do for us? That makes this formula a better predictor than it was before. And what do we call this? Instead of calling it simple linear regression, we call it still linear regression. We're still dealing with something we believe to be a linear relationship, right? Now we call it a multiple linear relationship. Now, there is a way in here, we didn't discuss it in class, so I'm not going to bring it up right now. There is a way in here. See, one of the things that bothered me a little bit about this was that, let's see, was that maybe some of these things are related to one another. In other words, confounders for the other. The information's already present with just one of them. So, for instance, perhaps visibility and inversion base height level might have some association already, right? So there's a way to use this analysis, and the order that you do the analysis in can have some impact. There's a way to do this analysis so that you can do your regression analysis first with, let's say, all but one of these variables, and then apply the second variable, apply the final variable afterwards to see if there's a change. The idea there, let's see what kind of change that you get in your regression analysis. The idea there is that you want to see if removing them and doing it separately from the others improves your regression analysis, suggesting, or doesn't, suggesting that that information from that is already in there from one of the other variables. In other words, one is kind of a confounder of the other. In other words, it's already influencing the other variable just in the numbers that exist already. Okay, so I think that's a good time to call it a day. I'm amazed that the two of you hung in there this long. So I hope that gives you a little bit more insight into correlation and regression, because it's an important topic. Coming up, as we finish up, we're going to look at one more version of regression, which is called logistic regression. Which the only difference there is that now we're going to be dealing with numerical variables. We're going to look to see whether or not a numerical variable like temperature or something else has a relationship to a categorical variable. Like, for instance, whether or not you're likely to be wind up in an emergency room under those conditions or something like that. Okay, so we'll take a look at it. Okay, good, terrific. I'm glad that helped out a bit. Okay, that's a good particularly good data set for this because they were all significant. Okay, guys, have a good morning.